Okay, today we're going to look at what happens with EMR waves. We're going to treat them as waves, and we're going to look at what happens when a wave hits a different surface. So the first thing we're going to look at is what happens when it hits a flat mirror. And it doesn't have to be a mirror, but we typically use mirrors. It could be water, it could be anything that's shiny and smooth. So the law of reflection basically states that the angle of incidence equals the angle of reflection. So a couple of key things to remember. We always measure the angle to the normal. So the incidence angle is between the ray and the normal, and then the reflected angle is between the ray leaving and the normal again. So remember, the normal is always perpendicular, and that's the angle we're talking about for angle of incidence and angle of reflection. So if the surface isn't flat, let's suppose it was sort of bumpy, it would still be the same. So right at the top we'd have our perpendicular surface, so our angle coming in would be equal to our angle coming out. But if our surface was sort of at an angle, and let's suppose our light ray comes in at the exact same angle, it would, depending on where it hits, it may be different. So the same ray coming in might scatter something different like that. So we're going to get rays coming in and going out at different angles, and therefore the image that we would see then will not be clear. It would be blurry and sort of distorted a little bit. And that's why if you look at water that's not perfectly smooth, we don't get a nice mirror reflection. It's kind of a blurry image instead. We're going to look at curved mirrors fairly soon, and we're going to look at drawing objects, but a couple of key things that we want to remember with just a flat mirror is our object would be what we're looking at in terms of a reflection, and we'll say our image is what we're seeing in the mirror. So our image we typically say is a virtual image because it would be behind the mirror, but normally we'd see it as the exact same size, exact same shape, just reflected side to side. And the reason for that is just the way the rays go from the original to the mirror. So let's suppose we have this moon-shaped object, let's say on your t-shirt, and you stand in front of a mirror. Your eye would see that image the same distance away. So whatever your distance is standing in front of the mirror, that's what the distance it would appear behind the mirror. So it's going to be the same size, same distance, same shape, but you can see of how the ray image would work. So if we look at the top of the moon, the angle going into the mirror would equal the angle coming out, but we don't see that. We see what appears in the mirror, so that's why we extend the line down. And then the same thing on the bottom. You can see here our bottom would go up to our eye at the same angle, and we would extend that down, and we see the bottom of the image. So pretty simple to draw these diagrams, and like I said, we're going to do more of them when we do curved mirrors, but for now the key idea is that the angles will always match, and that's why we see the image the way it is. If it was three-dimensional, like so let's suppose this moon shape, we were somewhere out in front of it when it would hit the mirror and hit our eye, that's why because the rays would sort of crisscross, that's why we sort of get the left to right reverse. So a couple of key things with flat mirror: image is reverse left to right, the image appears to be behind the mirror, that's why we call it a virtual image, and that's why we use dotted lines and a dotted image to show us that it's virtual. And the way we could test that is if we put a piece of paper where the mirror is, we wouldn't see anything. So because we can't see it, we'd call it a virtual image. If for some reason the image was projected onto the paper, like a overhead projector or something would work, then we'd say that's a real image. And we're going to get to those later on when we do curved mirrors. Our next topic we're going to look at is refraction. And refraction is what happens when the light rays enter a different medium. So in air, we say our light travels at 3 to the 8th, and it travels at whatever frequency and speed that it's going at. But if it hits a different medium, more dense medium, it's going to slow down, which would then cause the wavelength to drop, cause our angle to get bigger, and so on. So refraction basically is just the slowing or the change of mediums, which would then make our object look bent or kind of distorted. So you can see this pencil on the glass, the image kind of bends a little bit, and you can see it's sort of magnified in the bottom. So Snell came up with a formula on how to calculate this, and it's just basically a ratio comparing the two different mediums. So we'd say, in this case, let's suppose air, we'd say it has an index refraction of 1, and let's suppose the water is an index refraction of 1.33. So 1 would represent normal, 1.33 would be a little bit more dense, and then our formula is like this. And we only ever have to use two parts of it, so we could use the angles and the index number of the substance, or we could use the angles and the velocity, or we could use wavelength and velocity, or whatever. So any two of the topics. And the only thing you got to be careful with the formula is we just call it surface 1. So in this case, let's suppose we said the air was number 1 and water would be number 2. So we just got to plug in our numbers accordingly. You can see the N is the only one that the 1 and 2 are backwards. So the index refraction, like I said, is just a way of comparing densities of objects. So something like air is our standard, it's 1. And then the more and more dense we get would be higher and higher. So you can see water we used in the last question was 1.33. We get to something like diamond, we get to 2.42. So the higher the number, the harder it is for the light to travel through. So let's do an example. It says we got two indexes, 1.47 and 1.33. And it says it's entering at 43 degrees between glycerin and water. So let's call the top glycerin, and let's call that number 1. Let's call the bottom water number 2. So it says it's traveling and it hits at an angle of 43 degrees to the normal. So what's going to happen when it goes through into the water? So if we use our sine theta 1 over sine theta 2, that'll equal N2 over N1. So we just have to make sure we get the right angles and the right indexes in the right spot. So we'd have sine of 43 over sine of the angle that we're looking for. N2 is our water, so that's 1.33 over 1.47. So to solve that, all we have to do is cross multiply, go second sine of our answer, and we get about 49 degrees if we round it off. So you can see, in this case, I actually drew it wrong. So our angle of incidence was 43, and our refracted angle is 49. So as it hit the more dense object, it went to less dense, went from the glycerin 1.47 into 1.33. So as it hit the less dense object, it's going to speed up, and therefore our angle gets bigger. It moves away from the normal. And that's a good way to kind of remember these. If you go from more dense to less dense like we did, the wave will speed up and bend away from the normal. If we went from less dense to more dense, it's going to slow down and bend towards the normal. So with the speed of light, if we notice that in our formula we have V1 over V2, so the speed of light is going to change when it goes into a different medium. So our 3 to the 8 number that we use, that's for air, or more specifically in a vacuum going through space. So it would be a slightly bit slower in air due to the air particles and things like that, but we still just use 3 to the 8th for air. And you could actually slow it down by using different substances. So try to get it into a more dense subject. You should be able to get it to go a little bit slower. And over the years, scientists have actually dropped it to about 1 kilometer per hour. So they can almost bring it to a standstill just using refraction. And theoretically, we could go faster than 3 to the 8th if we could ever find a medium that's less than nothing, less than space, which is pretty tough. So that's why we use 1 as sort of our standard. And quite often that's how they'll figure out an index. They'll shine light through it and figure out how the light changes, and then from there they can figure out what the index of refraction is for that object. So let's do another example. It says we shine light into an object and we get 2.21 to the 8th, so it's asking what the index would be. So quite often in this case what we're going to do is compare it to air. So we're going to use N2 over N1 equals V1 over V2. So let's call 1 our air, and then 2 would be the unknown substance. So our N2 is what we're looking for, N1 for air is 1, speed for air is 3 to the 8th, and the speed for this unknown substance is 2.21 to the 8th. So all we have to do is cross multiply those, and we get an index of 1.36. Okay, so it's a pretty easy calculation to figure out what the speed is going to be in the new object, and then from there you can usually figure out the index. One last thing to look at, remember in Physics 20, we said that the wavelength can change in a wave, but not the frequency, because the frequency is usually based on what's creating it. So the sound of my voice has a certain frequency. It'll change and distort depending on certain situations, but my voice is still making the sound the same waves. If you're, waving a rope up and down, the source isn't changing. It's just how it's transferring is what changes. So the key thing is, remember, frequency will always be the same. So therefore, if velocity goes up, wavelength would go up. If velocity goes down, wavelength's going to go down. And we can usually use that to help us figure out certain kinds of things. So in this case, let's say we've got red light going through water, and it goes into glass. And I forgot to write down the indexes, but water we'll use 1.33, and for flint glass I think we use 1.42. And it doesn't really matter what the numbers are, let's just go with this. So if we use our formula again, N2 over N1 will equal wavelength 1 over wavelength 2. So we'll put in, let's call 1 our water, and 2 will be our glass. So we'd have 1.42 over 1.33 equals... water was number 1, so that'll be our 700 nanometers, and we don't even need to change the units, we can just leave it as that. So if we cross multiply and solve this, oops, I made a mistake, I think the index was supposed to be 2.42, so let's try that when we cross multiply. And that gives us an answer of about 385, approximately. So if 2.42 was our right number, we'd have 385 nanometers for our wavelength, and 385 we would see as probably an indigo blue kind of color, because 350, remember, is violet, so it'll be probably like an indigo would be my guess in terms of a color. Okay, and I think that's it. Yeah, so we'll stop there, and you can practice some of these questions in the worksheet.